All right, welcome to another topic in chemistry together online. So, our focus for today, you can start setting up your focus note page, is matter properties and changes. Now that we know what the subgroups of matter are and how we classify matter, the next piece of it is how do we describe matter and how do we know if matter has changed? Because that is what chemists do. They change matter, they make observations, they describe things that they're seeing. That's the whole purpose of chemistry, is matter and its changes. But properties are how we describe those changes. So go ahead and set up your essential question. What is the difference between physical and chemical properties and changes? And then also, what are the 5 signs of a chemical change? Because you'll see that for the definition of chemical change, it's hard to just know if that happened. But the good news is you will be able to observe one or more of these 5 signs, and that's how you'll know for sure it was a chemical change instead of a physical change. Go ahead and write down whatever date it is that you're taking these notes, and then remember you've got your spot for your for your acoustic questions and your spot for your summary, which will answer the essential question. And then remember, for this video, it's only the things in red that you need to write down. So that allows you to do some more thinking and processing and not just frantically writing everything down. Though the advantage of seeing this as a video, you can always pause the video if you need a little bit more time to write something or think about it before I go to the next slide. All right. Let's get into it. So there are 2 types of properties. If you want to write that kind of at the top of your notes, there are physical properties, which is a description that you make using your senses. So what is something making a noise? What does it look like? What color is it? Does it have a smell? Can you taste it? Does it have a certain texture? So what does it feel like? So those kinds of things are physical properties. They are definitely important when we do labs and you're trying to describe what you're seeing and write that down in your data table. So a physical property, something that you can get by just using your senses, are good things. So some examples, write down at least 3 of these. You can write more if you want to, but it would be things like, what color is it? What shape is it? What size is it? Maybe you can actually measure it with a ruler. Its density, will it dissolve in water? Is it ductile, meaning could you draw it into wires like these copper wires? Or malleable, think like aluminum foil. Could you bend it or shape it? What texture does it have? Is it smooth? Is it silky? Is it bumpy? What mass does it have? You could put it on a balance. So those kinds of things are physical properties. And you can imagine that some of those things are things that we measure or record when we do labs in chemistry. So those are physical properties. One example of physical property, so did you know that a pop machine or a vending machine is actually masters of looking at physical properties? So they test how much electricity a coin conducts because they want to make sure you're not putting in pieces of paper or plastic the same size of a coin to try to fool the machine. So first it tests the coin for conductivity, and then there's magnet and light sensors that determine, oh, this is a certain type of coin. So any type of machine that gives back coins would be using these properties, these physical properties, to make sure that they are the correct type of money. So if you're getting change back from a self-checkout at Target, there's all of these physical properties that are being tested to make sure you're getting back the correct thing. Or if you're putting money in, that you're giving us the correct thing. So those are physical properties. All right, the second type of property is a chemical property. And this is a description of an object's ability to take part in a chemical reaction or a change. So this is a changing room. So a description of an object's ability to take part in a chemical reaction. So is it going to react? Is it going to do something and change something about itself? And we're going to talk about chemical reactions in a little bit, but a chemical property, that's what it does. So this one's a little bit more specific. Here's some specific examples. Will it rust or not? Now, you might know that it would rust or not just because of prior knowledge. But if you're not sure if something will rust or not, you have to be able to do something to it. So you can't just tell by looking at it. Same with acid. If you want to know if something will react with acid, you have to put it in acid or drop acid on top of it and see if it will react, if something will burn or not. So again, you might have predictions of things that can burn because of prior knowledge, but if you're not sure, you have to do something to it. So being able to burn is a description. Will it go through that chemical reaction or not? And then same with mold. So those are some specific examples. So again, these are things that you can't figure out just by looking at them or using your senses. You have to do something to it and produce that chemical reaction or not, but both of them, whether it has it or not. So whether you burn something and it does or doesn't turn into flames, whether it does or not is still a chemical property. So that's kind of the idea. So a physical property means that you can figure it out just by using your senses or measuring it or something like that. A chemical property, you have to do something to it to see if it will go through a chemical reaction. So here's an example of a chemical property. The Statue of Liberty is actually demonstrating a really interesting chemical property. Maybe you've seen a picture of this, like of this version of the Statue of Liberty. It's actually made of copper. So when people built it way back, when at Staten Island, when they were trying to make something really important, they used copper because copper is a very fancy type of metal. However, over the years, copper reacted with the air to form that greenish color that we're used to. And so it's showing the chemical property will react with oxygen. And then you get that green color instead. So that's an example of a chemical property from your world. Okay, so that tells us about the difference between chemical and physical properties, which is the first part of our EQ. So go ahead and take your first brain break. Think about what you've written down so far. Does it make sense? Write a level 1 question. Remember, there is a Costa Questions guide on Schoology, but go ahead and write a level 1 type of questions, meaning it comes right from the nose. So you could define chemical and physical property. Or you could say, list the 2 types of properties. Those kinds of things, something that comes right from the notes. Go ahead and pause and write your level 1 question. Take a little break. And let's get back into it. Now let's talk about changes. So we would say that an object or a material or a substance or a chemical has gone through a change if its particles have separated, combined, or rearranged. Again, there are 2 types of changes, or just like there's 2 types of properties. There's a physical change and a chemical change. And since we're talking about changes, I have a question for you. What did the stoplight say to the car? Don't look, I'm changing. There's your little brain break, a little joke from you. Okay, so back to this idea. Any type of change means that something has happened to the particles. They've separated, combined, or rearranged in some way. Now, the difference between the chemical and physical change kind of depends on what's happening with those particles. So a physical change is when it looks different. The particles have maybe rearranged in some way, but it keeps its identity. The identity, or like the ingredients or the chemical makeup of those particles, does not change. So for example, if you paint something, all you're doing is transferring paint particles from maybe a can on top of something else, maybe a fence or a piece of paper or your fingernails. So all you've done is change the location of those particles, but the fence particles are still fence particles, the paint particles are still paint particles, the identity hasn't changed. Or if you cut something, so maybe you're serving, in this case, it looks like they're serving cake for some celebration. You cut the cake particles, you change their shape, and then you move them to another location, and then someone has them, in their hand or on their plate or eventually in their mouth, right? So cutting, all you're doing is changing the shape and the location of the particles. If you melt something, maybe you want to melt some butter to pour on your popcorn, it's still butter particles. Or if you break something, like when you break your arm, all of the identity of those particles in your arm, your bone, your muscles, your tendons, they're all still there. The identity is there. They're just maybe change their location, change their shape a little bit, and then they'll heal. So a physical change, it looks different, but it actually keeps its true identity. A chemical change, then, here we go. Here's what we've been leading to. This looks different because the particles have actually changed their identity. This is where we create new stuff. So chemists and engineers and people that are creating new medicines, new fuels, new flavors, new whatever, they are creating chemical changes. They're creating things that were not there before by using chemical properties. So using the fact that it will go through a chemical reaction or a chemical change to create something new. So you have a new identity. It has new properties now. A physical change could have new properties also. It could look different. It could feel different. But in a chemical change, it looks different because it's actually a new identity. So these would be things like if you let bread turn into mold, that mold is a new identity. It's not bread anymore. You wouldn't necessarily want to eat it. Baking a cake. So you mix all the ingredients together. Those would be physical changes. But once you bake it, that batter can't go backwards and turn, or after it's baked, the cake can't turn back into batter. So you've changed it. That's why it's safe to eat the cake, where we wouldn't generally eat raw eggs, but when you bake it, it's something new. Tarnishing is what happens to silver. Maybe you have some fancy silver jewelry or some fancy silver, like silverware, or a silver tea set, from maybe your grandma or something. And it starts to get kind of that discoloration, kind of like a greenish brown. That is the silver reacting with oxygen in the air, and it causes this thing called tarnish, which is like rusting, kind of what iron does. And then burning. So when you're done burning a marshmallow or a piece of wood, at the end, that stuff you have left over is not the same as the stuff you started from. So that's what makes it a chemical change. So something new has actually been produced, and that new thing has a new identity. So that's kind of the idea between physical and chemical changes. So go ahead and take a little break again and do a level 2 question. So level 2 questions, remember, are something that there's a hint in your notes, like maybe a definition, but then your brain needs to finish the rest of the answer. So a great example would be contrast of physical chemical changes, or sketch a picture of a physical change, like those kinds of things. Explain why a chemical change has a new identity, those kinds of things. So level 2 kind of question. Go ahead and pause, take a little break, finish your question, and welcome back. Okay, so then maybe you're thinking, well, wait a second. How do we know that the atoms or the particles or the object has actually changed their identity? How do we know that it actually is a new identity instead of just looking different like a physical change? Well, it turns out that science and chemistry gives us a hint. So there are 5 signs to tell us this is a chemical change or a chemical reaction. Those words mean the same. And so it turns out that I've got some fun demos to show you to represent how we know that there's a new identity. It's a chemical change instead of just a physical change. For joining me for chemistry demo time. All right, so the idea is that you already have understanding of the difference between a chemical change and a physical change. But if you think about those definitions, physical change looks different but keeps the identity. Chemical change looks different because it's a new identity. It's kind of tricky thinking about, well, how do we actually know it's a new identity? How do we know that there's new bonds forming, that there's actually a new chemical composition? That's kind of difficult to tell because sometimes it might not look a lot different. So the great news is that chemistry gives us some signs. So what I'm going to show you is what are the 5 signs that if you are observing some type of change, you know that if you see one or more of these things, you will know that it's a chemical change, not just a physical change. All right. So the first thing I'm going to show you is I have 2 chemicals here. This one happens to be called ammonium nitrate. It looks kind of like white beads, or kind of like, when styrofoam falls apart, like those little white beads. That's called ammonium nitrate. And then I've just put it in a baggie. And then the other one I have is calcium chloride, which kind of looks like white chalky sort of pieces, like crunched up kind of like hard pieces like that. So calcium chloride. And then what I'm going to do is I'm going to add some water to them. So right now, I'm going to give you a hint about what we're going to notice. Right now, we have, I'm using a digital thermometer. So you can see that, it looks like it's about 23.1, about room temperature. And what I'm going to do is I'm going to put some water in each of these baggies. And then we're going to see if we notice anything change. Okay, so you can see that one. I got some water in it. Looks a little bit cloudy. And then let me do the same thing. Some water in it. This is called deionized water, meaning that the only pieces floating around in it are water pieces, no other hard water, soft water kinds of stuff, like no other minerals. Okay, so remember that original temperature, all right? And then what I'm going to do is I'm going to put them in here. So you see what they look like now, just basically what you would expect. So right now you might think this looks like a physical change. But what I want to show you is I'm going to go ahead and put the thermometer in here, and let's see what we notice. Can you see it? There we go. All right, so look at that. So definitely an increased temperature, 42.1, 42.2, 43 a little bit. So definitely we see, there we go, let me get a little bit more in there. So remember, it started at 23, and look at that change of temperature. Not something you would have noticed just by looking. If you were here, you could feel it. It definitely feels warm. So a temperature change that happens on its own is a sign of a chemical change. All right, well, I've got this other baggie. Let's check out this. I did just clean this off in between. So let this get back. All right, it's cooling down. It's cooling down. I'm not going to wait for it. I'm just going to put it in here and see what we notice now. Look at that. So we are down to 4 degrees, 3 something. It just keeps getting lower and lower and lower. So remember, it started at 23, and then we got it up to, high 40s with that other baggie. And now you can see we're down to less than 1 degree Celsius we're using to measure in chemistry. So we end up with this really cold temperature change, even to the point of negative. Now, it's not frozen because it's not just water. Water freezes at 0 degrees Celsius, but it's even colder than that, showing you that these particles are doing something to change the amount of energy within their structure. And again, you would feel that this is pretty cool, like quite cold actually, based on that room temperature. So we see a temperature change. We observed it using a thermometer, and then also we can feel the container. Notice I didn't stick my hands inside the container, but if this was in a beaker, in a lab, you would be able to take the temperature or observe it by feeling the container. So when chemicals are mixed, so there's some type of reaction that you have started, and those particles change temperature on their own, that is a sign that you are creating some type of new identity. So a temperature change, either hotter or colder, when you didn't add it, you didn't heat it up, you didn't put it on a Bunsen burner, in a microwave, or a hot plate, but it happens on its own, that's a sign of a chemical change. All right, let's do the next one. Let me just kind of set some of these things aside here. Okay. This next one I'm going to do, so what I have here is I have a piece of cotton. Basically, it's kind of the cotton you would use like if you were going to make a stuffed animal, or you get it from a craft store. So just regular cotton there. And then what I have is something called sodium peroxide. Sodium peroxide, if you kind of see here, it looks kind of like little yellow beads a little bit. And I'm just going to make a little bed of some of that sodium peroxide and the cotton, and that's it. Okay, technically there's a little bit more. I'm also going to put a few drops of that same water I used in the last demo. Now, if you were close by, you might hear some sizzling happening. That's interesting. So there's like some sizzing and some fizzing happening. But then let's see if we notice anything else going on. Can you hear that sizzling? All right. Definitely there's something happening here. So the fact that we were able to produce fire by adding little drops of water tells you for sure this is a chemical change. Let's think about all the things that happen. For sure, a temperature change, like we just learned, if the temperature change happens on its own, we know that's going to be a chemical change. Fire implies that there would be a temperature change. But the other really cool thing you saw was light. So light being produced on its own from the chemical reaction is a sign that it's a chemical change. So this new stuff that I have here, it doesn't look like the stuff that I started with. So that is a sign that this is a chemical change, not just a physical change. Yeah, it looks different, but it looks different because it's a new identity. How do we know it's a new identity? Temperature change, light given off. And then there was that fizzing. We'll come back to that in a little bit. So definitely a sign that something new has been created. So we've got two signs of a reaction now. So if you're doing an experiment and you see a temperature change or you see light given off, this is a sign that this is a chemical change. All right, the next one I want to do involves a couple different liquid chemicals or solutions actually. This solution happens to be called potassium iodide. You can see that it really just kind of looks like water. It happens to be potassium iodide mixed with water. That's what makes it a homogeneous mixture, a solution. And then my other chemical I'm going to use is lead nitrate. Once again, kind of looks like water. So I'm using two chemicals that are called aqueous solutions, meaning the chemical is mixed with water to create a solution. And you can see they both kind of look similar. Now, if I were to ask a kindergartner, if I take something that looks like water and mix it with something with water, they might be like, oh, nothing interesting is going to happen. Or because they're in kindergarten, they might make up some wild story. Well, it turns out they might be right. Okay, so I pour in one of my solutions, and I take a look at my other solution, mix them together, ta-da! Chemistry happens, yay! Okay, so let's think about what happened. For sure, there is a color change. That's the thing that you noticed right away. But I also want you to notice, as I bring it a little bit closer, do you notice that there's kind of like some chalky collection at the bottom? That is a precipitate. The definition of a precipitate is a solid that forms from a chemical change between two solutions. So it's not anytime you produce a solid, right? So if you boil off water and there's like a crusty solid left behind because there was something mixed in the water, that's not a precipitate. A precipitate is the result of a chemical change between two solutions. We know it's a chemical change because if you looked at the way that those two solutions looked when they started, they looked clear, right? They looked like water. You couldn't see any particles in them. Now you can see these particles that have settled to the bottom. That is the precipitate. So this demo actually produced two signs of a reaction. A definite color change that was unexpected. So for example, a color change that's not expected is if I take a black marker and I color on a white piece of paper, it turns black, or any other color, or paint, or food dye, or any of that. Those are expected color changes. You haven't changed the identity, you have just changed the look of it. So that's physical change. But a color change, especially in addition with my precipitate, definitely an identity change. The starting chemicals looked different. The ending chemicals look different because it's a new identity. So we've got temperature change, light given off, color change that's unexpected with something else, and then this happened to be precipitate. All right, so we've got 4 of our 5 signs of a reaction. Let's go back, or let's finish it up with our last one. So what I have here is just a big metal tray, but then inside it, I've got hydrogen peroxide. Now remember that other demo with the cotton used sodium peroxide? Looks very different. Hydrogen peroxide you might even have at your home. Maybe you've used it for cleaning out cuts because the chemicals of hydrogen peroxide can kill cells. Now the tricky thing, the reason it hurts when you put it on your skin is that hydrogen peroxide doesn't know the difference between bacteria, germ cells, and regular healthy cells. So that's why you don't just use it to like wash your hands because it would kill any cells it comes into contact with. You would just want to put it on, a cut or a scrape or something to kill any bacteria. So that's what this chemical is, hydrogen peroxide. So I'm going to put some hydrogen peroxide in the bottom of this graduated cylinder. And you can see that, okay, sure, there's some little fizzy bubbles that form just because I poured it kind of fast. But other than that, I don't really see anything happening. So the tricky thing here is that this is a reaction that is actually happening. Hydrogen and oxygen are pulling apart from each other from the hydrogen peroxide. Now, you might be like, well, yeah, right, Ms. K, I don't see anything happening, right? So there's no signs of a reaction to prove that something is happening. Well, you might know, well, wait, hydrogen and oxygen, they're both gases. So maybe the reason we don't see it is because they're just floating away and we can't tell. So why don't I add some soap? If I add some soap, maybe that will trap some of those gases, and then maybe bubbles will appear, and then those bubbles will be the sign of my reaction. Okay, so let me mix that together. Okay, so definitely you see a little bit of bubbles, but now as I let it sit there, does it look like it's changing at all? Not really anymore, right? So either this is a dud of a demo, which I hope you trust that I'm not going to choose a dud of a demo for you, or there's something else going on. So the tricky thing about this demo is that it happens really slowly, and sometimes that's the case. Reactions take longer to happen depending on what is going on in that reaction. So I'm going to use something called a catalyst. Now, maybe you remember from biology that an enzyme is a catalyst that happens in a living cell to speed up reactions. Sometimes it's, we use it to get nutrients from foods. A catalyst is just something that speeds up a reaction. So I told you this reaction is happening, but it's happening really slow. Let's speed it up and see if we can get our 5th sign of a reaction. Let's see what it is. So I pour in my catalyst, and then what do we notice? Ta-da! Okay, so definitely something is happening now. Check that out. So now for sure there's bubbles, and then look at this. This tells us what? Temperature change, you're right. But the bubbles tell us that what is happening? Gas is given off. If you were here, you could smell it also. Now think back to that demo with the cotton. I told you that we could hear fizzing. That was also a sign that gas was being given off. So fizzing, bubbles, smell. If you can smell something that wasn't there before, that's a sign that a new identity has been given or produced, and it has a certain scent. So this one, you can see temperature change. You can see gas given off. And then there's also a little bit of a color change. You might be able to see kind of this yellowish color. So definitely signs of a reaction. So the stuff that's here is not the same identity as we started with. It looks like it would be fun to touch. The tricky thing though is that hydrogen peroxide might not all be used up. So these bubbles could actually be really painful the way that hydrogen peroxide is. So even though it looks really fun and like you want to touch it, it's not safe to touch it. Okay, so let's review really quickly. What were the 5 signs of a reaction? So if you're doing a lab and you're observing what's going on, these are the things you're looking for to see if there was a chemical change or chemical reaction. Did the temperature change on its own? So then you have to make sure you measure and observe before and after. Did the color change on its own? Is there a precipitate produced? Is there light given off? Is there gas given off? Those are the things we look for to decide whether or not something is a chemical change. Thanks for joining me for chemistry demo time. Bye. All right. Now, just in case you were so wowed by those demos that you forgot to take some notes, let's get you caught up. So go ahead and add this to your notes. This is the last part. 5 signs of a chemical reaction. The first one was temperature change. And remember, it happened on its own. I didn't add any heat. I just mixed chemicals together and they started to change their temperature. Light given off. So again, this is when the chemicals themselves are releasing energy in the form of light and you see it glow. Color change, though we usually say color change is not enough by itself. Why not? Well, because you may change the look of it, but not the identity. Like, for example, if I take blue paint and put it on my wall, I'm going to change the color of that wall, but I haven't changed the actual identity. So we don't know enough chemistry right now to say a color change by itself is a chemical change. But you saw in the demos that I did, usually color change happens with something else. Like, for example, in the demos, a precipitate was formed. Now, remember that a precipitate is a very specific definition. It's a solid that forms when 2 solutions are mixed. So like, for example, if you're boiling water and then the water all goes away and there's something kind of left behind because there was something mixed in the water, that's not a precipitate. That was just water leaving and solids being left behind because they didn't get hot enough to leave. A precipitate has to start with 2 solutions and then a chemical change happens when they're mixed and it creates a solid that wasn't there before, like that chalky yellow stuff that you saw. And then gas given off. So anytime you see bubbles or you hear fizzing or you smell a smell that wasn't there before, that's gas given off. And it's because the new identity has a scent or has a state of matter that was different than what you started with. So new identities. So these 5 signs of a chemical reaction are something that I want you to remember, not just during this unit, but moving forward. Anytime we do a lab, anytime you observe some type of experiment or thing happening in your world, you will know that it's a chemical reaction or a chemical change because of these 5 things, one or more of them happening. So to help you remember these 5 things, what I'd like you to do is I'd like you to do a little processing assignment. So in your notebook, trace a 5-fingered hand. So if you're right-handed, maybe trace your left hand. And then out of the tip of each finger, draw some type of picture or symbol that helps you remember the 5 signs of a chemical reaction. If you put some color in it, that's going to help your brain remember it. So in the future, when we're talking about experiments and we're trying to figure out if there was a new identity, we know that if we see one or more of these 5 signs of a reaction, that's how we'll know. And you'll remember them because you've got these pictures. Your brain remembers pictures better than words. It remembers color rather than everything being the same color. So adding in some color, these little pictures and symbols out of the tip of your hand will remember that there's 5 signs of a reaction, and the pictures will help you remember things like gas given off, light given off, temperature change, color change, precipitate. All right. And you could put that on the side of the notebook that you're not taking notes on. So that would be your output side. All right, that brings us to the end of our notes for today. So it's time for your last brain break. This is a level 3 type of question. Remember, these are those open ended, Brady kind of creative questions. So you could say something about predict which type of which sign of a reaction is most obvious to notice, or imagine what would happen if we never had physical changes. So some type of, again, open-ended prediction, imagine, critique, defend, those kinds of things. Write a level 1 question about our notes to kind of process what we just did. All right, so that brings us to the end of our fourth day of this first unit on matter. So here's the things I'd like you to work on next during our class time. Finish any Costa questions if you did not finish them from the video notes, and then now write your summary. Remember, the purpose of the summary is to ask yourself, what did I learn today? Did I learn what I was supposed to learn? By answering the essential question. I do have an assignment for you to start today. It's called the matter assignment. So if possible, depending on how much time is left right now during our class time, you could start this now. If you don't finish it, then you could finish it during your homework time after classes today. You can also, if you have any questions or you're confused or if it's not making sense or you don't understand what you're supposed to do, I have office hours today, tomorrow, and Wednesday. It's not due until, midnight Wednesday, not because I want you to be working on homework that late, but that's just kind of the default time saying that it's due at the end of Wednesday. So if you have any questions, use my office hours to get help. Don't be confused. It's okay if you don't know answers. Just make sure that you get help before we move forward. All right. Thanks so much for listening. We will see you at our next Zoom session. Bye.